Oh my gosh. Hey, how you doing? My name is Matt Lemos, and this is my exam 3. Come on in. So we have question 1 here, and it's regarding to like growing arrays, like we have down here for a visual reference of the octagonal and decagonal, and like we're talking about how they grow in their stages and so on. So we have our stage 1, our stage 2, our stage 3, stage 4, and over here we have our decagonal. Are you getting this? Are you getting this? We have we have stage 1, stage 2, stage 3, and stage 4. So we go back here, and we're talking about how they grow, and we go like 1, 6, 15, 20, 45. And I know this is a sample, and I'm just talking about it, but like it's like plus 5, and then plus 13, and then plus plus 9, plus 13, and then plus 17. But if we go back, and it's like, so it starts out plus 5, and then we have to because it has to be 6, be hexagonal, and then we go up and we go plus 5, plus 4, and I think it was 9. So we're adding the additional 9. The additional 4 to the 5, and then it's the same thing. It's like we take that 9 from here and you add another 4. So it's just growing in that aspect. And we look at the formula. We have 2n squared minus n, and so on. So if we plug that, it's like find that we see that 4 is half the 2 is half of the 4, and so we found it like that. So like we go over here, and like that's how I found this stuff, and it's like 1 to 8. It's like so we know octagonal is 8, so we have to have that 7. But then we look back over here, and we think it back to our arrays, and we see that it's like adding, but it's still shared like those original. So we have like take those plus 7, like we get that plus 7, and then we get that plus 7, plus 6, then plus 13, and so on. So like we get that growth, and that's where we get that 3n squared. But we also have to take away to do the shared, and that's why we have that minus 2n. And it goes over the same over here with the plus 9 to get to the decagonal. That plus 9 to get to the decagonal, and then the plus 9 plus 8, so we get 17, and so on. So we go back to what we were saying earlier. So we have that 4n squared from the plus 8 over constantly being added, but we also have to take into account what we already have, so that's why we have that minus 3n. And it's like we have these p-gonals to like find out what they really are, and it's like how they grow, and it's like, and so on and so forth. And yeah. Now for P, we're trying to find the number that P represents the number of vertices that are on the outside of it, but not within. Like the arrays build off one another in a way that there are shapes inside, but we're only counting the vertices to find this. So the P is the vertices. We take, and it's just growing as it goes. So it's like 3P minus 3. But if you extend it, we have 2P minus 3 plus P. That's the extended version to get it to grow and like how it would be. But I shortened it to 3P minus 3, and it goes on down the line. So here we're going to talk about the second question, and I'm not going to get into it because it's a lot to read, and I only have 5 minutes to explain all of this. But it's a word problem based on the finding a point that's equidistant between a gas station and Poly-Eyes, which would locate the park. So now if we come in close, we know we can use 2 methods to find it, or 2 different types of geometry. We have Euclidean geometry, and we also have taxicab geometry. First, we're going to start with Euclidean. In Euclidean, you're allowed to, quote unquote, pass the backyards and go in places you're not supposed to, essentially like you're flying. So we're going to find the shortest distance and a point that's equidistant. So to do so, we can find that the gas station and Poly-Eyes are in a perfect square, and they're 4 and 4, 4, 4 apart. So 4 blocks, 4 blocks, 4 blocks, 4 blocks, 4 blocks. So if we are using Euclidean and going places we shouldn't, we can use the Pythagorean theorem to find it. So we make our triangle. We have our triangle here, 4, 4, and then we draw that line in the middle. And we know 4 squared plus 4 squared. 4 squared is 16, so 16 plus 16 equals 32. If we square root 32, we get 5.6. But we're not looking for the length of this middle piece. We're looking for the equidistant middle point, which is right here. And we can find that that is 2.83 miles away from Poly-Eyes and 2.83 miles away from the gas station. So the park would be right there. Moving over to a taxi cab. We can't fly over things, so now we have to follow the grid lines, and we have to follow the grid lines, and we know that Poly-Eyes is 1, 2, 3, 4, 1, 2, 3, 4, 8 stops away from the gas station, and if you also take it this way, the gas station is 1, 2, 3, 4, 1, 2, 3, 4, 8 stops away from Poly-Eyes. So we know that they're both for a point that you could place it at each point. But to be sure, we make circles, and we see where they overlap. And since we can't use Euclidean and we can't get over the middle, we can find that in these 2 points right here, the park would be 1, 2, 3, 4 away, and 1, 2, 3, 4 away from Poly Eyes, and 1, 2, 3, 4 away from the gas station, and 1, 2, 3, 4 away from Poly Eyes. So we know it could be at either one of these locations. Now we come down here and we talk about where the park cannot be if we move the gas station. So I move the gas station over here, and this creates a little bit of a problem because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spaces, 11 blocks from the gas station, and 1, 2, 3, 4, 5, 6, 7, 8 spot, which makes 11 from the from Poly Eyes to the gas station. So if we tried to do this equidistantly, we could not, and we find that it would fall at 5.5 spots away, and to be 5.5 spots away, it cannot be because that's not an intersection, so the park cannot sit there. All right, so now we're on 3, which kind of hard, a lot of time consuming. We'll get into it. So we have the first question. We're talking about how far our crashed yacht is from the treasure. So the first question is, how far is the yacht from the treasure using Euclidean geometry? Well, using Euclidean, like I said before, you're allowed to do stuff you're not really allowed to in geometry and taxi cab, and you can fly over things and get there in a straight line as fast as you can. So we go back to using the Pythagorean theorem method, and we use and even though the space isn't in it, this whole line will be in it. So we can use all this space to equal out. So this length, the length of the treasure vertically is 9, and the length of the yacht horizontally from the treasure is 17. 9 squared plus 17 squared equals c squared, or our final answer. So 81 plus 289, which are the squares of 9 and 17, is 370. 370 squared is 19.24 miles. So if it was a straight line in Euclidean geometry, that is 19.24 miles. Your yacht is from the treasure. So now we have, how far is your yacht from yacht to the treasure using taxicab geometry? So we're using the fastest methods to get there. And so I did 2 methods just to be sure and just to double check. But like any like in anything, the quickest point excuse me. The fastest way to get between 2 points is in a straight line. So if we take all the way up to this, we only make 1 left turn, 1 right turn, and 1 left turn. We count all the blocks, and we get 26. We go 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. But even still, if we use the other side of the perimeter, 1, 2, 3, 4, 5, 6, 7, 8, and on, it's 26. So even if you're just trying to use the fastest way, the fastest number of blocks to get there would be 26 using taxicab geometry. Now here's the tricky part. We are determining, if you are allowed to travel on the grid lines and turn at intersections, how many different paths are there to get to the treasure? So we know that there's a lot. But how do we know which ones we're going to use? Because there's a lot of space here. So to determine we know we can't go, if we're starting at the yacht, it's a waste of time to go down or to the right. So the way I did it is I started at the treasure and I went to the right and down from there because that's the reverse of all that movement. So we came to the conclusion, all these dots here are the intersection we can use. So this doesn't matter, this stuff doesn't matter. So all we need to do is find the path from here. On to the time-consuming part. So there's a lot to get into, but when you start on the edge, you get your 1s and your 1s, and you just add up from the corners to 1 and 1 and 2, 2 and 1 is 3, and that on and on. You keep adding. I'm just going to talk about the stuff that might throw people off when they're adding together. So since we're not using this, we don't have to go any farther. But here's what we need to talk about is down here. So this line stays 28 from this point because there is no other way to get to it if we're using we're doing this ethically and not wasting any time. So to get to this point, you'd have to come down. And we're not doing that here. So this stays at 28. We're already in like this, and we're not making another move when we get here. So this line stays at 28, and this line up here, using the same methodology, stays at 7,532. And also this little 2-piecer stays at 42,252. So if we go around and we add all this up, and trust me, this took a very long time. Our final answer, I know it's very small, it's 2,012,332. That's the amount of different ways you can take to get from the yacht to the treasure while it's still using all of like correct movements and not going down or to the right. Thank you very much. And my name is Matt Lamos. Thank you for your time.